Hi, everyone. Do you have any questions from quizzes, homework, or lecture last week? Okay, so today basically we will cover chapter 4. And we can finish with the exercise for the exercise 4, problem 2, and possibly exercise 5. So those 5 are available on the website. And just I want to emphasize the fact that all quizzes and homework can be done with the code discussed in the slides. So in the quizzes and homework, we have so far seen chapter 1 to chapter 4 slides. So everything can be done with the codes discussed in the slides. And of course, if you know other functions, or if you see it's more convenient to use other functions, that's totally fine. But just if you want to catch up with class, only thing you have to do is just the review slides thoroughly and to understand the Okay, so we continue chapter 4. Maybe I will use the mic.
Okay, so last time we studied the PDF and the histogram. So histogram corresponds to PDF. So PDF is like this. The red one is PDF. And PDF, we have the empirical version of PDF. That is the histogram. So PDF is theoretical distribution, which explains the probability. The probability that random variable is between -2 and 2 is this area. So this area is maybe about 70% of the area under this curve. So you can see this probability is 70%. So this is the meaning of the PDF. But if we observe some observations, then we have the concrete, the histogram. So that means how many observations are between -1 and -2, and how many observations are between 0 and -1, and so on. And now that we are studying the cumulative distribution function. So cumulative distribution function is the function which explains the cumulative probability. So if we have x-axis and y-axis, then y-axis explains probability. So that is between 0 and 1. And the cumulative distribution curve, for example, like this explains the probability that random variable is exactly or below specific points. So if this value is 2, then this is the probability of random variable is less than 2. So in this case, maybe 75%. So probability is always between 0 and 1. And of course, this probability of x is less than something gets larger if this value gets larger. So this cumulative distribution function that goes to 1 as this number x goes to infinity, or x goes to negative infinity, that this goes to 0. Excuse me. Okay, so now that we think about the discrete version of this CDF, cumulative distribution function, so that is empirical CDF. So empirical CDF is defined by this formula. So n is the sample size in denominator, and the numerator is the number of observations with xi is less than x. So just if we have 10 observations, we count how many observations are less than x. So that is the cumulative distribution function. And last time we discussed this example. So suppose we have the 4 observations, then you can see that, for example, what's the empirical probability that x is less than 0.3. Then you can see that the 2 observations out of 4 is less than 0.3. So this is 2 over 4. So that is 1/2. So for any number, we can calculate this f hat, and that becomes this. So that is as a graph that we have just the step function. So the f hat x is 0 between x is 0, negative infinity to negative 1. So maybe I put this into so negative 1 that we have here. And negative 1 to positive 0.1, we have the value at 1/2. And the the positive 0.1 to positive 0.5, the value is 2/4. Then 0.5 to 1.3, the value is 3/4. Then after that, the value is 1. Sorry, value is 1. So this is 1/2. This is 1/4 and 1/2. And this is the 3/4, and this is 1. So this is f of x, f hat of x. So basically, this is the CDF, empirical CDF. Empirical CDF is a step function, so piecewise, the constant. Okay, so this is another example. So we generate the 10 random numbers based on standard normal random variables. And okay, so sample size is 10, of course. And then we can make a graph of empirical CDF by using this plot function with option type is equal to S. S stands for step. So with this, we can write the step function. And actually, this is x-axis. X-axis is this, sorted, so increasing order. So the 10 random numbers, but after generating random numbers, that we sort those 10 numbers in increasing order. And the y value is 1 over n, 2 over n, 3 over n, and so on. N is 10. So actually the 1 over 10, 2 over 10, 3 over 10, up to 10 over 10. So we just specify x coordinates and the y coordinates, then specify type is equal to S. And we know that the range for y is between 0 and 1. So we specify the y limit is between 0 and 1. So minimum value, possible minimum value for y is 0, and the maximum value is y. So we set it as is. So this is just the name of x label and y label. Then we get this one. So you can see this is the 0.1, and this is 0.2, this is 0.3, and up to 1.0. So this is the way to create empirical the CDF. And one thing we want to add is this line. So we know that the value of f hat is equal to 1 after this point. So we want to have this one. And also, if the value is less than this, maybe negative 1.4, we want to have this function. So we want to add these red lines, hopefully. And as far as I know, the default our plot function doesn't have this functionality. So if you wanna make the graph like this, this part and this part have been added, we have to create something. We have to do something creative. And okay, so this isn't really necessary to pass the course, but maybe the more complicated code can deepen your understanding in our language. So I want to introduce this graph. So yeah, so the original graph that doesn't have the left flat line and right flat line. So just that we want to add 2 more points to make this, the red part. So just we make the range for x from 1 smaller than the minimum value of x and 1 larger than the maximum value of x, so that we can draw the flat line on the right and on the left. And we will change some parameter values, default parameter values for figures. So the PAR, the parentheses. So this basically includes all default parameter values. So we just save it as some object, old PAR. And we change some parameter. So this is margin. So set margin size for the bottom and the left and the top and right. So you can check the default value for these numbers. And we just slightly changed because we put some labels, X labels and Y labels. Yeah, sometimes if margin is too large, sometimes we cannot really see the figure. And if margin is very small, we cannot see labels or the, so increments. And yes, then we do the plots. And here, the x1 is just the same as x, but we added 2 values, the here and the here. So these are new ones. And we put 0 to n plus 1 over n. So last time, 1 to n, but we added 2 points, the 0 and n plus 1. Then we can see the red, flat lines on both sides of the graph. And type is S, this is the same, this is the same. And the X limit that we specified, the X limit is slightly larger than, smaller than the minimum value of X, and slightly larger than the positive, the maximum value of X, so that to make sure that the graph has, wide enough to cover all necessary points. And X label X and Y label that we put the F hat of X. So F of X can be put very easily, just the F of X. But if you want to put hat, actually that we have to specify at first the hat function, then we specify the paste function. So paste function basically combines this hat of F and this X, the parenthesis X. Then after that, we put another function, expression function. Then finally, that we can draw this F hat of X. And we go back to the original parameters. We changed the margin parameters for margin size. So after we create the graph, to prepare for the next figure, regain the original parameter values. Then the final result is here. So basically, yeah, so that's it. Yeah.
I have a question.
Yeah, sure. Mhm.
When you're making the F hat,
Mhm.
do you have to put the F in quotation marks or the X in quotation marks to
Mm,
represent it as a string?
I think probably no. Yeah, you can try in maybe it depends on the situation. Yeah, I think that it's good to put the quotation if, especially if the just you want to see the letter as is, like the parenthesis X, and the hat of F. This is the still that we are applying some function to the something. So I think that we shouldn't put the parenthesis, the quotation mark here. And I think that with this code, I created this figure, so it doesn't return any error. But yeah, I think that in generally, if just you want to put the two quantity, for example, the XAB and the YCD, then you can put it in a quotation mark. Yeah, I think that it really depends on the situation. I think that this expression function that avoid that error. So usually that we need a quotation mark for paste function. But if we have expression function, probably we don't really need the quotation symbol. Yeah, maybe it also depends on the R versions. So maybe you can check your with your computer. Yeah, so generally we put the quotation, but in some cases you don't really have to. Yeah, I'm trying this. Yeah, I think that yes, the paste function basically needs quotation, but when we use expression function with paste function, you may not need the quotation. So yeah. If without expression function. So generally, it's pretty hard to guess that whether some function, such as paste function, the work under certain environment. So you can try. What do you think is correct? Yeah. Okay, so this is how we create the CDF. And why we study this cumulative distribution, empirical, the CDF, that is because based on CDF, empirical CDF, that we do some statistical diagnosis. And that is the QQ plot. So using the CDF and the empirical CDF, we can see if observations follow a specific distribution or not. So in statistics, often, we assume some random variables follows some distribution, such as x1 to x100 follows the normal distribution with the mean 0 and standard deviation sigma. And this is often the assumption, but many statistical results based on this assumption. So we want to check if this assumption is correct. And that can be done by QQ-plot. So at first, when we observe x1 to xn, for which we want to check the distribution of these, at first we order these observations x1 to xn. Then suppose f is the hypothetical CDF. For example, if we want to check if x1 to x100 follows normal distribution, then f is normal distribution. Then we make a plot of f inverse of I over n plus 1 and xi. So this is called the QQ plot. I think that we have the example in the next slide, but to be concrete, suppose we have 4 observations. So n is equal to 4. So n plus 1 is equal to 5. So we put 5 in the denominator. And we have the smallest, first smallest, second smallest, third smallest, and fourth smallest observations. So these are reflected here, 1, 2, 3, 4. Then we take f inverse. So f is the cumulative normal distribution. So these are the x-axis, and y-axis are these -1, 0.1, 0.5, and 1.3. So this is the QQ plot. And what does this do? Basically, these numbers, these 4 numbers, are typical realizations of this this distribution. So if the f is standard normal CDF, then f inverse of 1 over 5, 2 over 5, 3 over 5, and 4 over 5 are 4 typical realization of standard normal random variables. You can see that this do this thing. So that we have x-axis here, and we have PDF. Suppose this is the PDF, so f of x. So the graph is sorry, I'm not good at writing, but the graph is like this, maybe slightly different. Okay. Then 1/5, 2/5, 3/5, and 4/5 in the f. This is the f is cumulative distribution function. So basically, the area under this curve is capital F. So f inverse means the basically the area to the threshold. So that is the so f inverse is basically the quantile function. So that means if 1/5 is the given area. So suppose that this area is 1/5. Then f inverse of 1/5 is here. And another 1/5, we have maybe another 1/5 here. And this is the f inverse of 2/5. 1/5 plus 1/5 is the area of 2 over 5. And another one, maybe here. This is f inverse of 3/5. It looks a little large, so my graph is not very correct, but yeah, 1/5, another 1/5. Then this one is f inverse of 4/5. So basically, these 4 points are typical realizations of 4 random numbers with this distribution. Okay, so maybe this is a random variable, so the values are unpredictable. But based on this PDF, you can see these four are typical realizations. You know, the PDF is this, then you know, around here that we have higher chance to get the observations. So these four observations may be the most typical values. Maybe this is too small, maybe slightly larger around here, something like that. Yeah. Maybe center area is a little too large, so maybe like this. Then maybe the area is more like 1/5. So these observations don't have equal interval. It depends on this curve, so it doesn't necessarily have equal intervals, but these four observations are typical realizations. Probably the distance between this point and this point is closer than the distance between this point and this point, because we have more observations around here. So yes. So what does this QQ-plot QQ-plot does? So basically, we compare the typical realization of random variables and actual observations. So basically, the typical realizations means a kind of theoretical realizations. So we compare the theoretical values with actual values of some distribution. So that is what QQ-plot does. Yeah, so if we mention this, explain this in words, then this becomes this. So if the observations come from a hypothetical distribution, approximately the f of xi, i's largest observation, is equal to I over n plus 1. Or equivalently, the xi is f inverse of I over n plus 1. We just apply f inverse on both sides. So f inverse of f becomes identity, and f inverse of I over n plus I becomes this. So hence the QQ-plot is roughly on the straight line, y is equal to x, because these values, so these theoretical values, we compare the theoretical value with the actual values. So theoretical values and actual values should be close if the this assumption is correct. The assumption that the distribution of x is f is correct, then this value and xi, that should be similar. So that means the QQ-plot is roughly on the straight line, y is equal to x. Usually we put the theoretical value as x, the theoretical value in horizontal axis and the actual value in vertical axis. And the QQ-plot is roughly the y is equal to x. In this way, for example, we can check if observations follows roughly the standard normal distribution or something. And this is one example of QQ-plot, the observations, the four observations from -1, the 0.1, maybe the 0.5 and the 1.3. This doesn't have much information because only four observations, but maybe the next example is more informative. So we simulate the 300, the standard normal random variables. Then we make the QQ-plot. Basically, our f is normal. Normal 0, 1. Then what happens? Actually, we simulate random numbers based on this distribution. So the answer should be almost y is equal to x. Then actually, this is the result. So you can see the 0 is here, 0 is here, and maybe -2, +2, -2, and +2. And you can see the y is equal to x is basically this line. Sorry, this line. So maybe my writing is not good, but yeah, so this roughly follows y is equal to x. This is pretty good because actually we generated random numbers based on the assumption of standard normal distribution. Yeah, and if this curve is, so this plot is if like this. For example, like this. So you can see the actual observations are almost always between -1 and a +1. So this indicates that we have no, extremely large observations or extremely small observations. So it does not follow normal distribution. Or often we have different graphs, such as we have many outliers, some moderate observations, but also outliers. So this also doesn't follow normal distribution. Or sometimes that we have different plots, like we have this kind of curvature. So this around here, the slope is very small, but around here slope is large. So in such a case, the xi's do not follow the standard normal distribution. Okay, so here, the sample quantile, this is actual. And this is theoretical. So x-axis is theoretical. So this is xi. So this is f inverse of I over n plus I. Yes. Maybe one more example we see. So we generate random variable based on normal distribution, but different mean and standard deviation. So this y follows the normal, the 10 and the 5 square, but still it's normal. What happens to QQ plot for this? And actually the observations are almost on a straight line, y is equal to 5x plus 10. So actually the observations follow normal, then all points are roughly on a straight line. So you can see that this graph is almost the same as the previous graph, but you can see the numbers are different. So here 0, but the center is 10. And here maybe the -2 to +2, but here the almost like the -5 to maybe 0 to 20 mostly. So you have wider graph, right? And you can see that still the observations are almost normal, even though the mean is different and the standard deviation is different. So here it indicates the mean of observations is about 10, and the standard deviation is probably around 5. And so 2 standard deviation is about 10, right? So 2. So you can see that even it follows normal distribution with different mean and standard deviation. If straight line, then normal assumption is satisfied. The distribution is normal. If distribution is non-normal, we have specific pattern on this graph, like this, or like this, or like this. Yeah, we have some questions, the quiz questions today for those. Any questions?
Sorry, I have a question.
Sure.
So, if the QQ plot doesn't follow the like what we think it does the shape that it takes give us any clue as to what distribution it might follow?
Yeah, so that's a very good question, and it really depends on the case. Maybe I would discuss several examples. So maybe first example, maybe the tail is heavy, so we have more outliers. More outliers than normal. Then the QQ plot, how does it look like? Actually, this looks like more like inverse S-shaped, because this is theoretical. and this is actual. So, and actual values have more outliers. So we have some extreme actual observations compared to, theoretical line. Okay. So these are outliers, and outliers have, extremely small or extremely large value. So it's off trend line. So this is one typical case. And the second case is x1 to xn are skewed to the right. So data are skewed to the right, like income distribution. So that means skewed to the right means that if we make a histogram, so most people have moderate or low income, and some people have very large income. So in this case, the graph becomes some curvature, such as maybe graph of y is equal to x squared. I mean, the right half of y is equal to x squared. Maybe even we erase this. Right. So you can see a few observation has very large numbers, but the many observations are small. So in such a case, we have this kind of curvature. So like this. And the number 3, the data are truncated, or data are within the narrow range. For example, the test score distribution, even the distribution has large standard deviation, but still it's between 0 and 100. So in this case, clearly the observation should be bounded, so between 0 and 100. Theoretical values based on normal distribution, some observations are very small, some observations are very large. So maybe around here, it's almost straight line, but since observations are limited between 0 and 100, the final line looks like this, a kind of S-shaped. So based on the shape of QQ plot, you can see what the distribution of X is. So does this give some idea? Yeah, so we need to see some examples to see what happens to QQ plot. Yeah. So yeah, later we will check the QQ plot for some error terms of statistical model. And often the statistical model assumes the errors follow normal distribution. And we also study how to deal with it when it does not follow normal distribution. We have some remedies. So we change statistical models, or we change the method of estimation. And yeah, and also I want to mention why we use the QQ plot rather than we compare PDF with histogram. If we want to check the distribution of observations, it's more natural to compare the theoretical PDF with our histogram. So this is most fundamental way to do that. But the benefit here is the tail part. So you can see that the histogram and the PDF is almost 0 on the most left side and most right side. You can see the normal distribution is the bell-shaped curve. And maybe it has good information around the center. But at the tail part, this is almost 0. And histogram even hard to see what's happening on the tail part, because we have limited number of observations. So around here, we have many observations. And so we can check if this fit of this PDF and histogram is good. But around here, we have very few observations. So we cannot really see whether this follows normal or slightly more outliers here. But the QQ plot, certainly we see the lower part, the lowest part and highest part. So you can see if that we have outliers on both sides. So basically the same information in different graph, but the QQ plot is the better in terms of observing those extreme observations. Actually, at the center, we cannot really see how well this distribution fits. Probably histogram and PDF. Comparison of histogram and PDF is better to capture what's happening around the center. Yeah, but often in statistics, these outliers or extreme values are problems to estimate something. So that's why that we often check QQ plot. Yeah, and exercise 2 and 3, actually it's included in the exercise for exercise 5, but this asks to see what's happening if original random variable follows uniform distribution between A and B, and original distribution is T distribution in some case. Yeah, this one. Yeah. So this will be used in later chapter, maybe chapter 6 and chapter 11. So just important. Any questions? Okay, so the rest of the chapter 4 is not super serious, but several important, convenient functions. So we study some functions to summarize the data set. In chapter 1, we studied apply function. So this is calculating group means or group standard deviations and so on. So apply some function for multiple groups. That is the benefit of apply function. For example, it can be used to calculate the average of each row or each column, or mean of each row or each column, and so on. And here that we study aggregate and by function. So these are pretty similar functions. And first one is aggregate. So CO2 is the default data set in R. And this is, I think, some CO2 emission, maybe some environmental variables for some cities, some factories. And we have different plants. I think that this is, I don't know, the Quebec and Mississippi. Yes, Quebec and Mississippi. And we have several categorical variables, and we have some concentration of some chemical and some uptake of some variable. And if we use this aggregate function of CO2 by type, the type is this variable, then we can summarize the variables by type. So we have Quebec and Mississippi, and we calculate the basically the average of these numbers. Average concentration is 435 in both, and the average value for uptake is the 33.5 for Quebec and 20.8 for 20.88 for Mississippi.
I have a question.
Yeah, sure. Mm-hmm.
How is aggregate different from T-apply?
I think almost the same. The format is slightly different, but the I don't really see much difference. Yeah. Yeah, actually, I rarely use this aggregate function. Yeah. Yes. And another similar function is by function. This is almost the same here. And yeah, actually you can get almost the same answer. Slightly different output format. But we can use the we can also summarize the categorical variables. So that is the benefit of using by function, so that we can see how many observations in each categories. I think there is one quiz regarding this for today. Yeah, so apply function, aggregate function, summary function, by function. So the many functions have very similar functionalities, the slightly different output format. Yeah, and next one is the box plot. Have you heard of box plot? Probably you have heard of it in maybe middle school or introductory statistics class. So box plot is like this. So box plot is a plot to summarize the the univariate random variables, just the observations with single variable. And so it describes basically the median and the median and the first quartile and the third quartile. So first quartile is 25th percentile. And the Q3 is the 75th percentile. So that means basically the center 50% is here. Center 50% of observations are here. And usually this is just 1.5. Okay, so this is called IQR. Center 50% range is called IQR. So the length of this, if this length is 0.7, then this IQR is 0.7. And this is basically 1.5 times IQR, but it's truncated if observations are not there. So it looks probably this length is slightly less than 1.5 IQR. Maybe 1.5 IQR is from here, but no observations here. So that's why that it's truncated out here. So probably if you measure the lengths between here and here, probably it's slightly shorter than 1.5 times this length. And the same thing for the this one. So this dotted line is called the whisker of this box plot. So we can say the box whisker plot as well. And this is the smallest observations above 1.5 times IQR from this Q1. So we don't have any observations here. And if we have observations outside of this whisker, that should be denoted as this, sorry, maybe this circle. So these are outliers. So this one as well. For this specific graph, actually no outliers. So we don't really have the plots, but here we have one observation. See, here is outlier. Yeah, and okay, so the Q1 median Q3 makes sense. Why we take 1.5 times IQR? We don't really have specific meaning for this. Of course, if distribution, the observations follow a specific distribution, we can say something, 1.5 times IQR, that means, the coverage of 99.9% or something like that. But in general, that we don't really have meaning. So just we have such a custom that to describe the whisker plot, whisker as the 1.5 times IQR. All right, I got some questions maybe before. Let's get the Schrödinger box. Okay, I wish it. Okay, so it basically describes your uncertainty about the data. Yeah. Okay. Bosk and whisker plot. Yes. Yeah, so the meaning of whisker really depends on the distribution. So it doesn't have any general meaning. If you assume it's normal, then you can say something about the statistical property of whiskers. Okay, so that's box plot, and yeah, maybe I have to show how to make box plot. And so this is very famous iris data. So this is the 4 variables: sepal length, sepal width, and petal length, and the petal width of iris. And it includes 3 species of 50 observations each. We have 50 of Setosa species, and 50 of versicolor, and 50 of virginica. Yeah, in a Christmas party in a statistics department, one quiz asks how many observations are there in iris dataset. So this is such a famous dataset. So basically, this data is to distinguish species by these 4 variables. And the box plot, we can, yeah, this may be not the most convenient way, but if you want to describe the 3 box plot for each species one by one, you can just make a subset of iris dataset. Iris dataset is in the original, default R package. And species condition, we have to use double equal here. And then we set the 3 subsets. The D1 is Setosa, D2 versicolor, D3 virginica. And then we can make a box plot by this. And actually we overlay 3, not overlay, we put the 3 box plots in one window. To do that, we specify this option. So we align 3 figures as the 1 by 3 figures by row. So within the same window, even the regardless you are operating a system, Windows or Mac, then we have just one window which includes 3 graphs. So R specifies the range of this data set, and we specify the same range. Actually, if we did not specify this, probably the y-axis may have different scale depending on species. You can see the last species, it ranges from 5.5 to 8, but the first species, it ranges from maybe 4.3 to maybe 5.8. So R uses different scale for different species if you don't specify the range for Y. But this isn't really probably the most convenient way to make a graph. More convenient way is, maybe I want to explain a little more. So the parameter mf row that puts these 3 figures by 1 by 3 figures, and 1 is the number of rows. So just the 1 graph, the vertically, and the 3 means the horizontally how many graphs are there. So 3 graphs, so 1 by 3. Default is 1 by 1. So that's why if you put the more than 1 figure, actually the previous figure has been deleted, and we create a new graph. But if we do this up to 3 figures, then you can put it in a 1 window. Usually this isn't really convenient function because in this way, we don't really have enough space to put figures in 1 window. So we have probably we are likely to have more trouble about the size of margin or something like that. And another, I think the more convenient way is the box plot. This is values. These are values, and by species. By species. Just the tilde you can put. then you can make this figure. So it looks much better, right? So we have the name of species here, and we have the same scale, and we have 3-box plot. And another way is here. So box plot, we put the values for species 1. This is the Setosa. And this is values for Versicolor. And this is value for Virginica. So in this way, you can make almost the same plot, but we don't have names here, because we just extracted numbers and make a graph. So usually the second way is the most convenient, but if you control some other factors, possibly other ways are easier to get. Yeah, I think that even you put these species, still the coordinate is 1, 2, and 3. If you want to put some legend here, I think that, for example, this point is represented by X value of 1 and Y value of 7.5. Yeah, so this is how to create box plots. Do you have any questions? Tables. Yeah, maybe I go a little more. Tables. The tables are similar to matrices. And it can be transformed into data frame. So table object is very similar to matrix, but when you transform it into data frame, we have difference. Table can be transformed into matrix, assuming table is our contingency table. Okay, so just to see the example. So originally we have matrix, the 1, 3, 2, 4. Okay, and we can put the names on the matrix. We have the column names function, row names function, and the matrix looks like this. Then this can be, interpreted as we have 2 variables, X and Y. And the X is equal to A and Y is equal to C. We have 1 observation for such, combination. And X is equal to A and Y is equal to D. We have the 2 observations. And X is equal to B and Y is equal to C. We have 3 such observations. And BD, we have the 4 observations. We can interpret this table as this. And if this is table, you can transform this by, I think, some table function. So, yeah, as data frame, nothing happens. Yeah. So suppose that the table M in the above slide, so this one, this is a table. So this is originally made a matrix, but if this is a table, you can transform this as a data frame by using this as.dataframe function. So sometimes we want to replicate the original data set from summarized data. So that can be done by this table object. And that is probably not very useful, but the next one is very useful, how to summarize the data frame. So data frame to table, that is the usual way to go. Table to data frame, that is a kind of unnatural. So suppose that we have the data set. This is the MT cars data set, the specification of 32 car models, the MPG, number of cylinders, the displacement and horsepower and weight and maybe the quarter mile time and so on, the number of gears, number of carburetors and so on. And if we have this table, we can summarize just by typing the table of variable. We attach this data set and the table of gear, then we have 15 observations with the 3 gears. We have 12 observations for 4 gears and 5 observations for 5 gears. We have, the sample size 32, so total is 32. So this is the number of gears, 3, 4, 5, and these are number of observations, 15, 12, and 5. So this is very convenient. And even if we put the two variables are automatically summarized this table. So this means that there are 4 car types which have 4 gears and the 2 carb is what the I'm not sure, but there are 4 cars there which have 4 gears and a 2 carb. Carb is what I don't know, but the yeah. So you can summarize this contingency table. You can summarize data into this contingency table. So table of counts. Yeah, and also we have the xtab function and the tilde, gear, carb, data, MT cars. This get the same table. So usually I use the table function, but xtab also works. I don't know which is more convenient. Slightly maybe different if we put more than 2 factors, maybe. Maybe xtabs can deal with the more than 2 factors. And some other functions which have similar role, the ftable function, they're similar to xtabs, but it makes a flat table even when there are more than 2 variables. Usually the papers are 2-dimensional, so flat table is more convenient. And margin tables, that we sum up counts by rows. Yeah, so just a marginal distribution. And the prop dot table that transform a table of counts into a table of proportions. Just we divide by the sample size, so it doesn't do a significant job, but we have several functions. Yeah, so this is the margin table function. For example, original table is this, then we can get this. So margin table 2. 2 is the column. So we get this column. So the brown. So brown is the column. So the total is 198, and the blue, the total is the 101. So we have 101 and so on. Yeah. So that's it for today. And sorry, we don't have much time, but we want to do maybe one exercise. We do what exercise? Maybe exercise 5. Exercise 5, problem 1. We will do. Exercise 1. That you can download the Apple dataset. And this includes the adjusted daily stock return of Apple. And the we have to transform this variable into some return variable and make a histogram and make a QQ plot. And QQ plot based on the different distributions. They're based on the definition of QQ plot, and see which theoretical distribution explains the Apple stock return best. Yeah, so I will set up the breakout rooms, and yeah, we don't have much time, but maybe just 10 minutes. We have 24 people, so maybe we create 5 from the, yeah. Sorry, I got the question. Okay, that's fine. Okay, I will set the 5 breakout rooms, so enjoy your conversations, and I think that this room 3. Yeah. Okay, start. 10 minutes. Yes, sorry that we don't really have enough time. So maybe we can continue the next time about exercise 5. Yeah, and if you have questions, you can remain online, and otherwise, they'll see you on Thursday. And homework is due on Friday. Yeah.